Welcome back to this module on exploiting TLP to improve Unicore throughput. The topic of this lesson is interleaved multithreading, which is a form of hardware multithreading in which each cycle instructions from different threads are issued. This slide basically explains interleaved, also called fine-grain multithreading. The basic idea is to issue each cycle instructions from a different thread. So different ready threads dispatch an instruction in turn in a FIFO order every cycle. So I call this interleaved multithreading because that's what basically happens. Different threads are finely interleaved instructions by instructions. So again, if this figure here illustrates the execution of a single thread on a four-way superscalar, on a four-issue superscalar, this figure here illustrates block multithreading on a four-way superscalar where we have some cost in switching threads because we only switch threads when it encounters a long latency event. This figure here illustrates fine-grain interleaved multithreading because in the first cycle we issue instructions from the blue thread, thread 1. In the second cycle we issue instruction from the second thread, the red thread, and so on and so forth. A big disadvantage of this form of multithreading, this type of multithreading, is that the single thread performance is very poor. Basically, if we have n hardware threads, n hardware contacts, each thread gets only 1/n of the performance. So each thread can execute an instruction once every n cycles. So if we have two threads, this shows our canonical pipeline with our 5 pipeline stages: fetch, decode, execute, memory access, and write back. If we have two threads, then each thread gets only half the performance, while if we have 5 threads, then each thread gets only 1/5 of the performance. So if single thread performance is our main goal, this is definitely not the right multithreading approach. However, interleaved multithreading makes implementing forwarding somewhat simpler. Basically, if the number of threads is sufficiently large, if there are sufficient number of threads, then we don't need to forward. Let me illustrate in a little bit of detail what I mean by this. We assumed in the canonical 5-stage pipeline that the register file read takes place in the second half of the instruction decode stage, while the register file write takes place in the first half of the write back stage. That means that without multithreading, in between the execute and the write back stage, data must be forwarded from to the execute stage of the dependent consuming instruction. This is illustrated here, which again shows our 5-stage pipeline. In the previous cycle, in the cycle 3, this instruction that is executed in these 5-line pipeline stages reads all data from the register file, and so that it gets the right data, it must be the result from the previous ALU execute state must be forwarded to the execute state of this instruction. This shows the need for forwarding in the canonical 5-stage pipeline. How do we, with fine-grain multithreading, get rid of this forwarding requirement? Suppose we have 3 or more threads. Then in clock cycle 1, we fetch the first instruction from the blue thread, thread 1. In the next cycle, we fetch an instruction from the second thread, and in the third clock cycle, we fetch the first instruction from the third thread. That means that when the instruction from the first instruction from the first thread has finished, it has written back its result in the first half indicated by the dark coloring on the left-hand side of the write back stage in clock cycle 5. It writes back the result to the register file in the first half of clock cycle 5. And the second instruction of the very same thread reads the register file in the second half of that very same clock cycle. So if the second instruction is dependent on the first instruction, the number of cycles between these two instructions is large enough that the second instruction reads the correct data from the register file. Let's now have a look at how the hardware structure of our simple canonical 5-stage pipeline changes if we implement interleaved fine-grain multithreading. Basically, we have the same microarchitecture as for coarse-grain multithreading, block multithreading, except that data forwarding, if it is implemented, if it is required, must be thread aware. That means, of course, only instructions from the same thread can be dependent on each other, and therefore the forwarding hardware needs to know, is the instruction currently in the execute stage, is it from the same thread or from a different thread? So it implies that the thread identifier, the thread ID, must be carried by the forwarded values so that the hardware can detect, yes, this is an instruction from the same thread and I am dependent on it, I being an instruction. Furthermore, stage flushing must also be thread aware. The pipeline is not necessarily filled with instructions from the same thread, but from different threads. That means that only instructions from the thread that we want to flush must be flushed. Right? Same for taken branches and misses. We cannot flush all the stages without having a look at to which thread it belongs, because it may belong to a different thread, and we only need to flush the instructions that belong to this thread. Furthermore, the simplest example is that the thread selection algorithm implemented here in this hardware block called the thread selector is different. We don't schedule another thread when the current thread is stalled waiting for a long latency event. No, each cycle, hence the name cycle by cycle interleaving, we fetch from a different thread, and this is implemented in a round robin way. Furthermore, a small but yet useful optimization is that whenever a long latency event occurs, then the selector should put the thread that caused this long latency event aside so that it will not be scheduled, so that it will not be considered here. This completes this lesson. Thank you for watching. In the next lesson, I will give some examples of interleaved multi-threaded processes. Stay tuned.